Hi guys, welcome to another one of Untitled lectures, and today I'm going to talk a little bit about heat capacity and specific heat capacity, and we'll be going through some examples. I'll also be touching on something called the continuous flow method, so this video could be overlapping between CSEC physics as well as CAPE Unit 1. So when we talk about heat capacity, capacity means the ability to store something. And if we link it back to heat, heat is a form of energy. So when we talk about an entire body, we talk about heat capacity as opposed to something called specific heat capacity. So when you talk about the heat energy that is stored or absorbed by a body to change the temperature, that is the definition of heat capacity. It is defined as the energy required by an entire body to raise its temperature by 1 degree Celsius or 1 Kelvin. So what it means is that if we consider an entire body, we just want to know how much energy that entire body must absorb to raise the temperature of that body by 1 degree Celsius or 1 Kelvin. So we talk about capital C being the heat capacity, and it is the energy to cause a change in temperature. So it is joule per Kelvin or joule per degree Celsius. A couple of times students have said to Miss, what is the SI unit? The SI unit of temperature is Kelvin, so therefore if you consider it in SI units, it's joule per Kelvin. Now if instead of considering this entire body, right, how much heat is supplied to this entire body to raise its temperature by 1 degree Celsius, I just wanted to find out a little portion of that body, right, or a unit mass of that body. Then that leads me to something called specific heat capacity, and that is denoted by common C, right? Now by definition, specific heat capacity is the energy required to raise the temperature of a unit mass of a body by 1 degree Celsius or 1 Kelvin. So because now we are going to include mass, our equation becomes E over m delta theta. So then the unit would be now joule per kilogram per Kelvin, SI of course, or sometimes it's quoted in joule per kilogram per degrees Celsius. Now, a lot of times I have seen in my experience students getting errors in transposing. So let's look at each of these, right? So as everything, life is better with a formula pyramid. So if you are one of those students who always have issues with transposing, you could use the pyramid. So all you do is that you cover whichever one you want to determine, right? So if I wanted to get C, I cover C and I get E over m delta theta. Here, if I wanted to get energy, it's the heat capacity by delta theta, okay? Now, a lot of students confuse heat capacity with specific heat capacity. An easy little trick is that if you look at your unit and you don't see any kilograms, then this is big C. And if you examine your unit here and you see kilograms or grams, then that is little c. Now, many times CSEC has asked you what is the relationship between heat capacity and specific heat capacity. So if you look here, heat capacity is E over delta theta. If you look here, specific heat capacity is E over m by delta theta. So basically, you are seeing that C, common C that is, specific heat capacity, is your heat capacity, right, over m. So it means that capital C is equal to mass by specific heat capacity. Now, when you are asked to differentiate, because sometimes they could ask you what's the difference, you just express it in terms of mass, because one of them deals with the amount of heat energy absorbed per unit mass, while the other one talks about the heat absorbed by the entire body. Okay, so now let's look at some questions, right? And we're going to start off with basic examples. Okay, so in example 1, we're going to say a body of mass 2 kilograms is heated from 20 degrees Celsius to 40 degrees Celsius. Okay, so the first one is a body of mass 2 kilograms is heated from 20 to 40 degrees Celsius. If the heat capacity is 4000 joules per Kelvin, determine the energy needed. So you have the heat capacity and you want to get energy. So we'll go back to our C is equal to E over delta theta, right? So you want to get the energy, right? And what are you given? You're given C and you're given the change in temperature. Now, sometimes in a question, not all of the data needs to be used. So let's go. So E is equal to C by delta theta. Now, I don't need the mass in this case because I was given the constant as heat capacity. If my constants were given a specific heat capacity, well, yeah, I could do that, right? So I am using the change in temperature here as 20 degrees Celsius. Now, note that a change in degrees Celsius and a change in temperature in Kelvin is the same thing. All right, so I have C and I have delta theta. So let's work out E. So E works out to be 4000 by 20, and that's 80,000 joules. Now, another thing I want to point out is the relationship between energy and power, right? And we didn't really address that prior. Many times you can use an electric heater, electric element, to heat something. And the power is a rate of change of energy. So we could now look at the electrical power as the rate of change of energy, because many times in these questions you might be asked to determine, like you're given the power of the heater and then you are asked to determine what is the time of heating or the energy provided. So power is energy over time. Power is measured in watts, which is joule per second. Another thing as well is that here you have power is energy over time. So energy, if you cover energy, it's power by time. Okay. All right. So let's look at another example here. Let's look at water now. Let's say that 200 grams of water is heated from 30 degrees Celsius to 50 degrees Celsius in 20 seconds. If the specific heat capacity of water is 4200 joules per kilogram per degree Celsius, what is the energy needed and hence calculate the power of the heater. So lots of things are going on in this question, and as I've always taught my students, we apple pick. Apple pick is just my term of saying you read through a question and you pull off the pieces of data, right? So here you're going to say, okay, 200 grams is mass, right? But always look, whenever you have a mass and you have specific heat capacity, you look at that correlation, kilograms. So this is 0.2 kg. It is heated from 30 to 50. So delta theta is 20 and the time is 20 seconds. So you have specific heat capacity C, and you want to get energy and you want to get power. Now if you get energy, power is energy over time, and we have the time. So let's get the energy. So you have mass 0.2 kg, delta theta is 20 degrees Celsius, time is 20 seconds, specific heat capacity is 4200 joules per kilogram per degree Celsius. I want to get two things, energy and I want to get power. So whenever you are undergoing a change in temperature, the universal equation stands. E is equal to mc delta theta. Alright, so let's work through. So it's 0.2 by 4200 by 20. Right? So 0.2, alright, so that works out to be 16800 joules. And now we want to get power. So that's energy over time. 16800 over 20 seconds. So that's 840 watts. Okay. Now let's look at another way that we could use specific heat capacity, and actually it's one of the experiments to determine specific heat capacity. Now this method is called the continuous flow method, and it is more ideally used at the Cape level, right? And the concept of this is, how do we get C, right? So the method basically uses a tube, and you have a certain mass of water flowing in, right? And you have the liquid flowing out at this end here, and here you normally have a thermometer, right? And here you have a thermometer as well, and in between you have a heating element, and you encase the entire apparatus in an evacuated tube to reduce heat loss by convection. Now the main advantage to this method is that you do not need to know the heat capacity of the components of the apparatus itself, right? So it means that you are ignoring the heat absorbed by them. Okay, so you have an initial mass of water, M1, right? And that mass of water is flowing through the heater of power P in some time, and you have a certain temperature of the water entering and the water exiting. So in a certain time T, you're going to have the water flowing over your heating element, and it's going to increase in temperature, right? So steady state is basically where you are maintaining a constant temperature difference across the ends of your apparatus, right? So we're using the formula power is energy over time, right? So power is equal to m over T by C delta theta. Now I have chosen to divide just the mass by T because you are looking at the rate of flow of a certain mass of water. So you're going to have the same time that you're heating different masses of water through the same temperature difference. So the only thing that's manipulated is the power of the heater. And you're going to repeat this, right, at least twice, and you're going to basically formulate equations and eliminate them, right, to determine what is C. So let's go. So let's say I have an initial mass of water M, right? So M1 over T, and I have a certain power, P1 supplied, my specific heat capacity, and I have delta theta. I'm going to let E be the energy lost to the surroundings. And this is equation 1. Now let's say I repeat my experiment, but I choose another mass of water, but I am letting T and delta theta be the same, right? Because this is in keeping with something called steady state. All right? So now I have to adjust the power. So that's M2 over T, C delta theta, and I'm assuming my energy lost will be the same. So now we're going to say equation 2 minus equation 1, right? Because we let M2 be greater than M1. So P2 minus P1 is M2 on T minus M1 on T by C delta theta. And the two energy losses will be subtracted, which is why we did not need to consider the value for the heat capacity. So now when this is eliminated, you could make C the subject. So it's P2 minus P1 over M2 on T minus M1 on T by delta theta, right? And this is very accurate because you are using a platinum resistance thermometer that measures a very small change in temperature.